Hi, this is Mrs. Clark, and today we're going to talk about light and quantized energy. Quantized, that's a pretty crazy word, but if you think about the word, it starts with quant, which really kind of means quantity. And so we're going to actually be looking at light and other forms of electromagnetic radiation and trying to figure out what kind of wavelengths and numbers are represented by it. So what really is light? So what we have all around us is electromagnetic radiation. And the word radiation has some weird connotations, kind of usually meaning something that we should be afraid of. But if you are afraid of radiation, you might not be able to leave your house because the radio waves that go through your body and your car that you catch anytime you turn on a radio, those are radiation. The light all around you, that's electromagnetic radiation. So really, this is just a term for little waves or packets of energy that flow through the air around you, some of which you can be detected by your human eye. So let's get a little bit more specific. Electromagnetic radiation is energy that travels and spreads out as it goes. And it actually has this dual nature as both particles and waves. Sometimes it behaves as a wave, and sometimes it behaves as like little packets of energy that are traveling through the atmosphere. And there are a lot of really intense scientific explanations for this, but we don't really have to get too deep into that right now. So we're just going to go ahead and move on. So when you think about a wave has amplitude. And amplitude represents the brightness of the light. So kind of the taller the peaks are in the wave, the brighter the light is to your eye. There's also wavelength, and wavelength will represent the color of the light. If you think about wavelength in the fact that last time you were at the beach, if you went out into the ocean and you were bobbing up and down on the waves, think about when the waves come really slowly and how kind of peaceful that can be in the ocean. Then imagine that the waves come faster and faster, and so the length between the waves is shorter. And so if you think about that example, you might realize that the shorter the wavelength, the more energy there is in that wave. Now there's one other concept that's kind of interesting. And the interesting thing is that if the wave is vibrating kind of up and down, it's polarized one way. If it's vibrating side to side, it's polarized a different way. We can actually use its polarization in a few different ways. So one way is through the original kind of 3D glasses. So what they would do is they'd have two separate projectors, and each would project in a different polarization of light. And then you would wear the little glasses, and the glasses on the left eye would only let through one polarization, on the right the other polarization. And between them, when your eyes see two slightly different images, it actually allows for distance, giving your image that you're seeing a 3D interpretation by your brain. And so that's one use of 3D glasses is through polarization. Another place that you see polarized lenses is just in sunglasses. And a lot of times, if you've ever noticed glare off of, the road or off of water or even just off of a tabletop when you have dinner outside, that light as it hits the counter kind of comes up all at the same angle. So if you wear glasses that are designed not to let in any of the light that comes from a certain angle, it can actually reduce glare. And fishermen use it because the glare off of the water can be cut out, and you can actually look in the water and get a better view of the fish if you're wearing polarized lenses. We also use these on our smartphone glass a lot of the time to reduce glare, but that means if you wear polarized lenses and you have a smartphone, there's a chance that if you turn your smartphone a certain way that you'll reduce your ability to actually see through the glass because your polarized lenses and the glass are both cutting out the same wavelengths. So let's get a little bit closer look at the electromagnetic spectrum. So here is kind of a general look all the way from gamma rays to AM radio. So right now I want you to look at this and think about what has a longer wavelength, a gamma ray or AM radio. Take a look. Gamma rays have a 10 to the negative 14th wavelength, and AM radio has a 10 to the 4th meter wavelength. That means AM radio is waves are so long that they would actually go longer than a football field for one wave. Gamma rays are so small, they're actually about the size of the nucleus of an atom. So each of these have really different wavelengths, which leads to a different intensity and a different level of energy associated with them. This is why we're afraid of gamma rays, but we're not really afraid of AM radio. You'll see there's a really small portion here in the middle, and that portion is the entire spectrum of visible light. So this diagram and most diagrams actually take that visible light and expand it so that you can better see all of the different light. So infrared, after infrared we get to what we call visible red. So these are the wavelengths of light that our brain can actually see, interpret, and consider to be a color. And so the least energetic color that we can see is red, and the most is violet. And if you've ever heard that some animals might be able to see into the infrared range or into the ultraviolet range, it's just that their eyes can actually pick up wavelengths that are either a little bit wider or a little bit shorter than the ones that our eyes can pick up and our brain can interpret as light. So if we look really closely then, this is actually kind of a reversed image of what we just saw. So we're just looking at the same data the opposite way. And if we think about radio waves, they are as big as a skyscraper. Whereas as we get smaller towards AM or microwaves, those are like the size of a human, or we're getting small like a butterfly. Infrared waves, which are actually the waves that you emit as kind of heat, are only as big as the point of a needle. So now we're getting to really, really tiny waves. And then we get some that are like small multicelled organisms. Ultraviolet rays are down to molecules, X-rays are as big as an atom, and gamma rays as big as a nucleus. And so it's kind of interesting because these rays here on the right side are what we call ionizing radiation, which means that they're intense enough to knock electrons out of their bonds and can cause cancer or errors in DNA replication. And that's why these ionizing radiation waves can be dangerous, and we try to avoid interacting with them as much as possible. I mean, X-rays are important, but we want to limit our exposure to them, especially if we have a career where X-rays are part of our everyday life. Here's a little bit more information about some of the different things on the electromagnetic spectrum, and you're free to pause and take a look. But I'm going to go ahead and keep moving. All right, let's go ahead and apply this and try a problem. Think about the last time you were at the dentist's office. You probably got X-rays done, and X-rays have a wavelength of 1 angstrom. And then you might have been listening to the radio, and radio has a wavelength of 3.25 centimeters. And if you looked out the window of the blue sky, you might have noticed it has a wavelength of 473 nanometers. Yes, you might have noticed it, I'm sure. Just kidding, but I do know that blue is 473 nanometers. So the question is, what is the frequency in seconds to the -1 power of the electromagnetic radiation from each source? So first of all, let's talk about frequency. Frequency is an ability to talk about how often something happens. And so one way to say that is per second. Well, per second is like 1/seconds. How would you represent 1/seconds with an exponent? Well, if you remember from your math class, any number on the bottom of a fraction can be represented at the top if it's to the -1 power. And so s to the -1 is just a frequency in per seconds. To do this problem, we'll also need to know that the speed of light is 3 times 10 to the 8th meters per second. So our plan is to use C equals wavelength times frequency. And our solution will be found first by changing all of our units to meters. If you'll notice, the speed of light is in meters, and since we're going to plug that into our calculation, we have to have all of our values in the same unit. So let's go ahead and change those. I'll give you angstroms. That 1 angstrom is 1 times 10 to the -10th meters. But what I want you to do then is figure out how many meters is 3.25 centimeters and how many meters are 473 nanometers. Go ahead and pause and work that out on your own. Welcome back. All right, so if I take my 3.25 centimeters and multiply by 1 meter for every 100 centimeters, I'm going to find that I have 0.0325 meters as my wavelength for the radio. Then I'm going to have 473 nanometers. I'm going to multiply 1 meter equals 1 times 10 to the 9th nanometers. If you are using the King Henry method in order to kind of mentally remember how far away everything is, remember that micro and nano are each 3 moves of the decimal away, and so that power of 1,000 for each you have to take into consideration. And when you calculate that, you'll find that the wavelength of our blue sky is 4.73 times 10 to the negative 7th meters. All right, next step. What we're going to need to do is solve our equation to isolate the frequency, which is the variable we're looking for. So here is our equation. First, I'm going to divide out the wavelength, and I get this equation here. Once I do that, I can plug in my value for the speed of light, which is c, just like this. Now I'm ready to solve for my unknown in all 3 of my problems. So right now, I want you to go ahead and give that a try for each of these 3. Go ahead and pause it, plug into the equation we just put together, and solve to find the frequency. All right, welcome back. Hopefully you just solved, and let's take a look and see if you got it right. So for X-rays, we're going to go ahead and plug it in like this. For radio and for sky, here's our equation. So for X-rays, we're going to solve by plugging in our meters for X-rays. And there's our meters for radio and for the sky, which are our blue sky. And finally, if we go ahead and solve each one here, the X-ray frequency would be 3 times 10 to the 18th. Our radio frequency would be 9.23 times 10 to the 9th. And the frequency of blue wavelength of the sky is 6.34 times 10 to the 14. Now, one other way to say per second, because it is a kind of confusing thing, or seconds to the -1, which we did say that we should solve for, this is also known as hertz. So you've probably heard the term hertz before, but that is another way to represent seconds to the -1. And as far as I'm concerned, you can write per second, you can write hertz, or you can write seconds to the -1 for our frequency unit. All right, so let's talk a little bit about some of our ways to apply this information. So a spectrometer is a device that we can use in order to split up light into its component parts so that we can see what that light is made of. If I show hydrogen, hydrogen will have one color that my eyes see because it can't separate all the different colors within it. So if you pass it through a prism, you'll get all of the different colors. So if you've ever seen one of those stones that hangs in a window and shoots tiny little rainbows all over the room, that's a type of prism. So that the light can come in, it travels through at different speeds, and as it comes out at a different angle, you can separate the light and get a rainbow. If that light was not from the sun, which is created with all of the colors in it, if it was just one single element, you would get this kind of fingerprint that represents that element's light. So when I look at hydrogen, in this example here, I only get a little bit of light because hydrogen only has one electron. And so as that electron is excited in 4 different ways, I can get 4 different beams of light released as it releases the energy it's absorbed. For mercury, I get quite a few more bits of light, and also for strontium here, because they have more electrons, which can be moved around when they're excited using energy. So, like I said, most of the light around you is actually made of all of these different wavelengths combined, but in a spectrometer, just like the crystal that was in the previous slide, you'll actually see the wavelengths of light split apart based on their frequency. Each bar of light represents a specific wavelength. And a rainbow occurs when light passes through an object where all of the wavelengths of light travel at different speeds, and it causes them to leave the crystal at a different place, and that separates out the light so that you can see each component part. So here's an example of what we can do. We can actually take elements and we can excite their electrons. So here we have a flame test. This is going to be like a lab we do later this week. And we're going to put certain elements, certain ions of those elements in a flame. And as we heat them, the electrons inside that element get excited. And as they're excited, they move up to a higher energy level. Remember that electrons fill each energy level very carefully so that they're as close to the nucleus as they can get. They have the lowest energy. But if you put energy in, they actually can jump up to much higher energy levels. So as they move up to higher energy levels, they then fall back down. And as they fall back down, they emit energy as a photon. And so, as I just said, so electrons are normally rushing around in their ground state electron cloud. But if I apply energy, whether it's from a Bunsen burner or whether it's from some other electromagnetic radiation, an explosion, anything, that energy is absorbed by the electron. The electron moves to a higher energy state called the excited state. As it falls back to the ground state, the energy is released as electromagnetic radiation, and sometimes we can find those radiation that we can actually see in the visible light spectrum. And that is what we get colored light from. You can see this in a really good example every 4th of July when the fireworks go off and you can see all the beautiful colors. All that's happening is they're exploding ions of salt that emit that energy from the explosion back out as photons of light. So every element actually has a specific set of photons that can be emitted based on its electron's ground state and the excited state it goes to. This emission spectra is like a fingerprint, and only that element will have this set of lights. And a photon is a packet of electromagnetic radiation, or what we kind of think of as a packet of energy. One of the most amazing applications of this is our knowledge of space. So if you've ever wondered how they know what elements are out in space, they look at other stars and they can actually isolate the light coming from that star, put it through a very specialized prism, and identify what elements that star is made of based on the kind of fingerprint spectra of light coming from that star. So even though we could never travel to another star for so many reasons, we can actually find out what they're made of from millions and billions of miles away. Now, if you think about those energy levels, this is kind of more of a visual approach. If we have an electron in one of these, this is the Bohr model, which we know is an easy way to visualize how these work. But remember that each energy level has not just spherical areas that electrons travel, but also the different funky shaped orbitals that we talked about in class. And so, but as electrons jump up to a higher state, okay, so here in this visible series, you might see an electron that jumped all the way up to here, all the way to here, here, or here. On its way back down to the ground state, it releases energy. So that's emission. As the electron takes in the energy, it's called absorption. So we can say absorption is up, emission is when it comes back down. Another way we can think about light is as a particle. And the photoelectric effect is a phenomenon where electrons are emitted from matter because electromagnetic radiation hit them. So when we get visible or UV light, it actually has so much energy that even though it doesn't have kind of a solid factor to it, that light can knock an electron away from its location. So here's that equation, and here are the three definitions of the variables in that equation: energy, Planck's constant, and frequency. So let's go ahead and do this one last problem, and then we'll be done. I know you're pretty much out of space, so you can just flip over your notes or work them out in a separate place for this one problem that we have. So this is a tricky one because it is about a microwave and we want to know what the energy is, but we're given wavelength. So if you look at the equations, neither equation includes both wavelength and energy. So what we're going to have to do is solve for both. So first, we can use this equation on the right. We can plug in wavelength, and we can find frequency. Then we take the frequency that we find on the right equation and plug it into the left. Okay, so first we're going to find the frequency using C equals wavelength times frequency, and then you can plug that into energy equals Planck's constant times frequency. We already solved the equation for frequency just a few minutes ago, so let's go ahead and take a look at that, which was the speed of light divided by the wavelength equals the frequency. Let's go ahead and plug the speed of light in, and that should be in meters, remember. All right, so here's our equation, and all we have to do is swap out the frequency for the meters. Now, remember, we had to change that wavelength to meters, so 1.20 centimeters is not going to work out for us. We had to change that into meters first. Go ahead and pause while you solve this. And you should have gotten 2.50 times 10 to the 10th per second, second to the minus 1, or hertz. So we can take that variable and we can apply it to the second equation that we learned. So now we want to plug our frequency that we just found into E equals Planck's constant times the frequency. So remember, Planck's constant is 6.63 times 10 to the negative 34th joules times seconds. And we just found out that the frequency is 2.50 times 10 to the 10th per second, or hertz. So we have our equation, E equals hv. What I want you to do right now is go ahead and solve for the energy and see what you get. All right, welcome back. Hopefully you got this right. Let's take a look. So here are our two variables plugged in. And what you can see here is that if this is in seconds and this is in per seconds, the seconds cancel. So our units in our answer should just be joules. And in fact it is. So we should have 1.66 times 10 to the negative 23rd joules. But what does this mean? And I think one really important thing that you should strive to do is, as soon as you finish a mathematical problem, try to come up with a sentence that explains that problem in regular words. So I want you to kind of look back at the problem, look at this number, and try to write a sentence that explains this in words. So pause right now and try that. All right, welcome back. Your sentence may vary from mine, but it should be something like, this means that one photon of microwave radiation contains 1.66 times 10 to the negative 23rd joules of energy. In math, we end with a number and that's it. But in chemistry, that number represents something bigger than itself. And so it's really important to kind of look back, think about what that number means, and then if we write it out, what we do is we not only learn the math, but we learn the concept behind the math. All right, guys, so that's it. And I look forward to talking more about this with you in class. Thank you very much.